a grounding system for a house with a meter at the pole, the meter and main breaker at the pole are likely the main grounding electrode for the house. At this location, the neutral and ground conductors are bonded together. At the house panel, the neutral and ground conductors are isolated. This means the neutral conductor carries current only, while the ground conductor provides a path for fault currents and static electricity to the ground. You can connect a ground grid system to the existing grounding system at the house panel to enhance overall grounding performance. There are two connection options for the ground grid. Firstly, if possible, run a ground wire from the ground grid to the ground bar in the house panel. This will create a direct connection between the grid and the main grounding system. Secondly, if running a wire to the house panel is not feasible, you can connect the ground grid to the grounding rods that are already bonded to the neutral at the main grounding electrode. However, this option is less desirable as it may create a longer current path. Even after connecting the ground grid, the main grounding electrode, which is the meter and main breaker at the pole, will remain the primary grounding electrode for the house. The ground grid system will act as a supplemental grounding electrode, providing additional grounding paths and improving the overall grounding performance. The purpose of grounding is to provide a low impedance path for fault current to return to the source, allowing overcurrent protection devices to operate and clear the fault. A ground grid system, also known as an earthing grid, consists of interconnected bare conductors buried in the earth. This grid provides a large surface area in contact with the soil, which helps to reduce the overall resistance to ground. A lower resistance to ground improves the effectiveness of the grounding system by providing a more efficient path for fault current. Supplemental electrodes are additional grounding electrodes that are installed to improve the overall grounding performance of a system. They can be used to reduce ground resistance, provide multiple grounding paths, and enhance the effectiveness of ground fault protection. According to the National Electrical Code, NEC, a grounding electrode system must consist of one or more of the following electrodes. Firstly, a metal underground water pipe in direct contact with the earth for 10 feet or more. Secondly, a grounding electrode conductor that is connected to the metal frame of the building or structure. Thirdly, a concrete encased electrode consisting of at least 20 feet of 1/2 inch or larger steel reinforcing bar or 4 American wire gauge copper conductor encased in at least 2 inches of concrete. Fourthly, a ground ring encircling the building or structure consisting of at least 20 feet of bare copper conductor not smaller than 2 American wire gauge. Fifthly, rod and pipe electrodes which shall not be less than 8 feet in length and shall consist of electrodes of pipe or conduit that shall not be smaller than 3/4 of an inch trade size, or of rod of steel or iron that shall be at least 5/8 of an inch in diameter. Sixthly, other listed electrodes. The ground grid system can supplement these electrodes. The size of the grounding electrode conductor is determined by NEC Table 250.66 based on the size of the ungrounded service conductors. The grounding electrode conductor connects the neutral point of the service to the grounding electrode system. The equipment grounding conductor provides a path for fault current for equipment enclosures back to the source. It is sized according to NEC Table 250.122. Based on the rating of the overcurrent protective device in the circuit. Grounding and bonding are essential for electrical safety. Grounding provides a path for fault current, while bonding ensures that all metallic parts are at the same potential, reducing the risk of electric shock. Grounding electrode systems are used to connect electrical systems and equipment to the earth, providing a path for fault currents and helping to stabilize voltage. The requirements for grounding electrode systems are specified in NEC Article 250. A main bonding jumper is used to connect the equipment grounding conductor to the grounded conductor at the service equipment. This connection ensures that fault currents have a low impedance path back to the source, allowing overcurrent protective devices to operate and clear the fault. The size of the main bonding jumper is determined by NEC Table 250.28 based on the size of the service entrance conductors. When installing a ground grid, it is important to consider soil conditions, as soil resistivity can affect the performance of the grounding system. Soil resistivity is a measure of how well the soil conducts electricity. Low soil resistivity is desirable as it allows fault currents to flow more easily to ground. Soil resistivity can be affected by factors such as moisture content, temperature, and the presence of salts and minerals. In areas with high soil resistivity, it may be necessary to use ground enhancement materials to improve the effectiveness of the grounding system. These materials can help to reduce soil resistivity and improve contact between the grounding electrode and the soil. The ground grid should be installed in accordance with NEC Article 250 and any applicable local codes. It is important to ensure that the grid is properly connected to the grounding electrode system and that all connections are secure and corrosion resistant. Regular inspection and testing of the grounding system is recommended to ensure that it is functioning properly. Ground resistance testing can be used to measure the resistance of the grounding system to earth. A low ground resistance indicates that the grounding system is effective at providing a path for fault current. If the ground resistance is too high, it may be necessary to add additional grounding electrodes or take other measures to improve the grounding system. A qualified electrician should perform all grounding system work to ensure that it is done safely and in accordance with all applicable codes and regulations. Improper grounding can create a serious safety hazard. It is essential to use proper materials and techniques to ensure that the grounding system is effective at protecting people and equipment from electrical shock and damage. Grounding is a critical aspect of electrical safety. It protects people from electric shock, provides a path for fault current, and helps to stabilize voltage. By following the requirements of the NEC and using proper grounding techniques, you can ensure that your electrical system is safe and reliable. When dealing with electrical systems, always prioritize safety. Work with qualified professionals and follow all applicable codes and regulations. Proper grounding is essential for protecting people and equipment from electrical hazards. The ground grid system acts as a supplementary grounding electrode, enhancing the main grounding electrode and improving overall grounding performance.